A few clips ago, I talked about wireless network access using cellular. Let's dig a little deeper into 5G technology. The cellular client is known as the user equipment or UE. This might be a smartphone or cellular-enabled CE router. The UE connects to a cell tower, which is part of the radio access network or RAN. Remember the discussion about concentric rings being used to extend a service provider network across a wide geographic area? Now imagine a cell tower connected to each one of these routers in the ring. All those towers together constitute the RAN. Most cellular consumers are trying to access some centralized resource, such as a web application or a video stream. To achieve that, the RAN forwards traffic to the user plane function or UPF, which is essentially a router. The UPF connects to an upstream data network or DN, which typically leads to the internet. In a privately operated cellular network, the DN represents an enterprise network, but these deployments are rare. I've built one using 4G, and it wasn't easy or cheap. What I just described to you is the path that data takes from your cell phone to the internet. You might be wondering about how the phone actually connects and how various policies are applied. The 5G architecture strictly decouples data forwarding from control services. The access and mobility management function and the session management function, AMF and SMF respectively, play a key role in connecting UEs to the RAN. The specific protocols and interfaces involved are out of scope for this course. Just understand that these functions allow carriers to onboard, track, and migrate cellular users while they roam. The authentication server function and policy control function, AUSF and PCF respectively, are auxiliary services that don't directly interact with the data forwarding items. Authentication ensures that only trusted clients join the network, and the policy control can apply traffic prioritization to improve user experience. There are several more control services I am omitting for brevity, but they all can communicate laterally using various application programming interfaces or APIs. For example, the AUSF can notify the SMF if a client fails authentication so that the SMF can purge the session from its database. By decoupling these functions into different microservices, it creates a standards-based, vendor-neutral architecture that can massively scale. I'd argue that the biggest benefit of cellular communications is mobility. Perhaps you've deduced this already, but in IP networks, a device's IP address is both its unique identifier and its location identifier. It's similar to a physical mailing address in real life. If you move to another house, your mailing address also changes. To provide seamless roaming in cellular networks, 5G relies on tunneling between the RAN and the UPF. Consider this conceptual example. A large carrier has multiple cell towers connected to an access ring within a geographic area. The UE is currently connected to Tower 1, which forwards traffic to the UPF, providing network access to the UE. Because there are many more towers in the RAN than there are UPFs, a tunneling protocol called General Packet Radio Service Tunneling Protocol, or GTP, is used to connect the RAN to the UPF. Just like we saw with CAPWAP tunneling for Wi-Fi, GTP allows wireless traffic to be transported to a central location when egressing from the cellular network. When the UE roams from top to bottom, it must retain its IP address during that process. Once the UE completes its migration to Tower 2, Tower 2 will tunnel traffic back to the UPF, again using GTP. The control services like AMF and SMF are notified of this change and facilitate the handoff from Tower 1 to Tower 2. By the way, UPF to DN connections often exist in the aggregation layer to service a geographic region, but this is highly dependent on the geography. I hope you're starting to see a pattern between different network architectures regarding their use of tunneling to solve mobility and multi-tenancy problems.